All right, now let's see some specific examples that will allow us to make better assessments of the impact of the unloaded Q on the filter performance. So here's an example of a fourth order classical Chebyshev filter. The coupling diagram is shown right here, as we have discussed in the past. It's a filter that basically has a relatively wide fractional bandwidth. If you see its center frequency is actually 1 gigahertz, and the fractional bandwidth is 0.1 gigahertz. So it basically has a substantial fractional bandwidth. So it's a relatively wideband filter, in other words. And here you can actually see its insertion loss, or the filter response to be more precise, for building this filter with different resonators. So the black line is the one that represents infinite Q. It's the ideal synthesis. And then progressively we go for worse and worse resonators. So the red line will give you the 500, and the blue line will actually give you 100. And finally, there is a green line that will give you 25. What is interesting to actually notice here is, first of all, the insertion loss obviously becomes worse. And for example, if you build this filter now with a Q of 25, your insertion loss is basically 10 dB, which honestly, for most practical cases, that's useless. That filter would be totally unacceptable. But in addition to the insertion loss becoming worse, which is something that most engineers know and expect, there are two additional things that most of us tend to ignore. The first one you will find out is that the matching performance gets worse. So the matching level actually is reduced. And you can clearly see that, for example, of the case of the 25Q, the S11 actually becomes worse. Now, at the level that I'm showing that here, it might not be as big of a deal because you're going from 20 dB to 15 dB, right? You can tolerate that. But in most practical cases, you don't have this much leeway. So you barely may have a matching of 15 dB or 12 dB, and with effect of the loss, you might end up with like 8 or 9, which starts becoming unacceptable. The other part is selectivity, which we're going to see in a less forgiving filter more precisely. But even here, you can see that the selectivity of the filter actually becomes worse. So that means that a specific frequency away from your center frequency, so here we're talking about, for example, 15% lower frequency, the Q of 500 will actually give you a rejection of 42 dB, while the Q of 25 will give you a rejection of only 32 dB. That's 10 dB difference. Right? In this graph, it might not appear as much, but that's 10 dB difference. So that means you could be completely out of spec just because of Q. And so because of that Q now, you may have to, unfortunately, increase the order of the filter. So maybe because you don't meet the spec, you might have to go from fourth order to maybe sixth order. But guess what? Sixth order will actually push and punish the insertion loss even further. So basically, you can't win unless you invest in a better resonator. Now, this is an interesting graph because it takes the calculation that I showed you before with the coupling matrix and compares it to the actual insertion loss of the filter. And the reason I'm showing you to this graph is because I want you to see how accurate the coupling matrix actually captures the effect of the loss. So it's practically perfect. So you don't have to worry whether what we're discussing here works or not. And this is another little graph that basically tells you, for those of you who are used in seeing poles and zeros on the complex plane, it basically tells you what exactly happens for the poles when the loss is there. They're basically getting shifted to a more negative value in the real part. And the amount of shift is actually related to that sigma factor that we basically calculated before. So if you want to synthesize an H function, a transfer function based on poles and zeros, you can very quickly do that as well. Now, let me show you another example which will allow us to explore a little bit more the issue of non-uniform loss distribution. So again, most of the times that's not a question, but here we have worked out an example where 3 of the resonators have a good Q, and one resonator, here is basically the Q of 3, or here is the Q of 4, basically has a different Q. So just to see essentially what effect this might have, in one case scenario, this different resonator is placed in position 3. This is basically the case 1 that you see right here. And the red line shows the case where that different resonator is placed in position 4. So what you will basically see there is that there is a slight difference in the filter performance. So you can see, for example, that when we place this different Q at the very end or closest to the source or the load, the passband response is affected more than when you basically place it before. Now, even more interesting than that, I think, is the question of why people might bother about creating uneven Qs. And this essentially has to do with fixing the transfer function. What I mean by that is that, as you might see, and I'll go back here, as you might see here, when you penalize the Q, you basically destroy the transfer function of the filter by essentially penalizing its selectivity. Essentially, by unevenly distributing Q, you can get some of this back. So it's possible to, instead of having this line, this green line that you see here, it's possible to have something that looks closer to a more ideal filter response. You can't buy back your insertion loss, but you can buy back some of the selectivity. And that's the main reason why people have come up with synthesis approaches for uneven Q distribution. So if you're interested in that, I can give you some more papers to read about this, but this is the main reason why people are doing that. This is beyond the scope of this class, but you might see it out there. Now, let me show you an example where the penalty of Q is even more obvious. So this is, again, our fourth order filter, same response that we had before, same frequency as what we had before, but now our fractional bandwidth is actually much less. The fractional bandwidth here is actually only 1%. Now, if you repeat the same exercise as I showed you before, the results are actually quite dramatic. Things are not progressing linearly. They're actually becoming quite bad. For example, look at now the green line that represents the Q of 25. Before we had about 10 dB. Now we have about 55 dB of insertion loss. Practically non-existent, right? I mean, practically the filter is non-existent. It doesn't actually make any sense except that it attenuates things. To show you here more precisely the selectivity of this filter, the penalty, I should say, in selectivity, I have plotted the normalized S21. So that basically means I shifted all the curves to 0 dB at the center frequency. So you can basically more clearly see how bad the selectivity of the low Q filter is. So this is the low Q case. You might also recall that Q of 25 is actually quite decent for on-chip components. In fact, it's very difficult to make good inductors with Q much higher than that on-chip. So now you might start realizing more precisely why we don't do channel filtering right after the antenna. So let me remind you some of the things we had discussed in the system level discussion. We had said that right after the antenna, we will normally select our band, right? Then we will down convert with our VCO, and finally we will have basically channel selectivity here. So channel selectivity would be not in the first stage. The first stage would basically be more band selectivity. Now you can see why, because fractional bandwidth of 1% is actually quite a bit higher than channel selectivity. Channels normally will actually be quite a bit less than that. So practically, if you were trying to do channel selectivity at the very first stage, you would introduce so much insertion loss that nothing would work anymore. So this is a pretty dramatic thing. Look at, for example, even with a quality factor of, let's say, 100, which is kind of the limit of off-chip components, for this case, you're still at a 20 dB insertion loss. The second reason that I want you to show you this graph is because later on we will be discussing acoustic filters. And acoustic filters are amazing in the sense that the quality factor you will get there is actually above 2000. And it's precisely for the reason that this graph actually underlines is that we actually have to reach this high of a quality factor. So I would say in general, in most systems, unless you get a Q in the order of 500, 1000, 2000, depending on the exact fractional bandwidth you have, you're practically out of luck for this first filter. Now, this is the comparison I promised you before regarding the different estimates for insertion loss. So I'm giving you basically for the two filters that we just studied, the one that had fractional bandwidth of 10% and the one that had fractional bandwidth of 1%. I'm giving you the loss that we get from the formula I just presented before. So this is basically the second column right here, as well as the insertion loss as estimated by the coupling matrix technique. So you can see that as long as our Q is reasonably high, practically for the first case above about 100, the relative error between the two is very small. But for the 1% case, actually only for the Q of 500, the relative error is pretty good. In the second case scenario, remember that we had something in the order of 20 dB loss, way too high, even with a Q of 100. So basically our error is basically unacceptably high for the empirical formula. But as long as your insertion loss is not too high, so in other words, as long as the number you will see here from this graph is maybe between 1 to 5 dBs, you can probably trust this formula that you're getting something decent. Now, so far I have given you a few remarks regarding insertion loss of band pass filters, which are very, very common, but I also wanted to give you an example of what happens, what is the penalty of low Q for a band stop case. So here I have the fourth order Chebyshev band stop case. The coupling diagram is here. We've actually spent quite a bit of time explaining why this coupling diagram represents a band stop case. I won't repeat that discussion here. But what is interesting to note here is that now your insertion loss is of course penalized in the out of band. So here is, for example, the insertion loss of the 25 out of band, and here's the insertion loss of 100 out of band. So you have to worry about this part. In addition to that, you will basically worry about loss of selectivity, and this happens basically towards the edges of that filter. Now, even though in this graph is not shown explicitly, this will also limit the maximum attenuation that you will be actually able to get. So the maximum attenuation will also be penalized in those type of filters. Now let me show you a practical example of a filter realization that the focus of this example is to give you some hints of how you might be able to estimate the quality factor of the resonators if you can only see the full response. So before we have actually learned how I can estimate the quality factor by making a weakly coupled measurement. And sometimes you will have this luxury, but some other times you might not. So this is an example essentially of a filter shown right here. It's a microstrip filter, and actually we have not learned yet how to design this type of filters, but you know the concept. So the concept is creating resonators. So this is one resonator here, this is the other resonator here, this is the input and this is the output. So these are gap coupled resonators, very similar to what we have seen, but the difference is that it's not an edge coupling, it's more of a parallel coupling. So you overlap enough area here to basically create the correct coupling between the two. So the math we have not seen yet, but the concept is known. So if you can only get, and this is an actual measurement here, if you can only get the actual measurements, you will be able to basically measure exactly the insertion loss that you have in your band. And in this case, it's about a dB. So what you can do is then you can also look at the shape factor of the filter. The shape factor of the filter is actually defined, I guess I'll use my black line here, is actually defined by how quickly the filter actually rejects. So once you have the shape factor, and let's say this is a second order filter, what you can do is you can very quickly go back to ADS and simulate, or any other simulator you have, and simulate essentially a band pass filter that is second order, and start varying the Q. So the Q here will be variable until you basically hit the insertion loss that we have. So that's a very common technique, and this is what has been done here. So basically the the quality factor is 85. Another estimate you can do is you can basically take the coupling matrix equations I had just gave you, and again take these diagonal elements that we were discussing before, change the sigma, since you know fractional bandwidth and F naught, until you basically hit the performance. So this is also what has been done here. This is the coupling matrix lossy approximation, which again gives you a Q of about 85. So either way, you can basically do that. And this is commonly done in real life if you don't have an unloaded coupling measurement.